So let's solve this problem. We have a piston cylinder assembly. Maybe we sketch it like this. And we have a piston sealing it right there. And inside we have refrigerant 134A. Let's just say the system here. And it's refrigerant 134A. It has an initial temperature of -24. Maybe we organize it by a couple different ways. Maybe I make a quick little table. I understand that it's going to have an initial state 1 with maybe a pressure. I like to put it in this order in kilopascal, temperature in degrees C, and it comes in with the -24 degrees C initial temperature and initial quality of 95%. And the refrigerant is slowly heated to a final state. Let's call state 2 the final state, where the pressure is 6 bar, so that's 600 kilopascal, and a temperature of 140 degrees C. While the refrigerant is heated, its pressure varies linearly with specific volume. What does that mean? Well, I can make a sketch, and if I have the pressure, specific volume, and maybe the specific volume starts at this value, V1, and this pressure, P1, and if it would increase, maybe go out to here to V2, and the pressure may go up to P2, right here, P2, then it would be a straight line. It would be a linearly varying pressure as a function of the specific volume. This would be one where the pressure is going up and the specific volume is increasing. A lot of times that doesn't happen. As the pressure goes up, the specific volume decreases. So maybe I switch and maybe I start and say that state 1 might be out here and state 2 may be right there. So this would be state 1 and state 2, and the system would be like this, where it's being, as the pressure goes up, it's being compressed. The specific volume's decreasing. So V1, V2, this is P1, P2. Either way, that's what it means that it's linearly varying with the specific volume. The refrigerant 134A, we want to determine the work and the heat transfer in units of kilojoules per kilogram, and there are the answers. So we take a look at it for a while, and we're asked to find this cap Q during the process divided by the mass, and the cap W for the process divided by the mass. And so that gives us the units of kilojoules per kilogram for each of those terms. Okay, well, we're probably going to be interested in the specific volume, and we're probably going to be interested in internal energy. The units on specific volume, meter cubed per kilogram, and internal energy in kilojoules per kilogram. And those are properties. And why would we be interested in the V and the U? Well, if we're interested in this work per unit mass, then it's basically the area under the curve on a PV diagram. That's our boundary work as the refrigerant 134A pushes against that piston and changes volume. So maybe it's doing this. Maybe the final state is more compressed, and so it's at a smaller specific volume. And how did that happen? Well, it just magically happened by increasing the pressure. Here I'm showing increased mass, increased weights on the top of that piston as it undergoes the process from initial state 1 to final state 2. And again, the mass was added a little at a time as it continued to change volume to get this linear profile. Okay, well, if I was interested in calculating this work per unit mass, then from first principles, the work 1 to 2 per unit mass would just be that pressure, the integral of PdV. Well, because it's a nice integral like this, it's the average pressure times the final specific volume V2 minus the initial specific volume V1. Okay, what's the average pressure? Well, if I have the pressure at 1 and the pressure at 2, I just add them together and divide by 2. So I need to get this pressure right here. Well, we're given that it's refrigerant 134A, we're given the temperature and the quality, so it's like I know that its temperature and quality is given, so it's in a two-phase region, and I go to the appropriate table for refrigerant 134A, which is table A10. Okay, so I go to table A10 and I look up the saturation pressure as a function of temperature. And so I look down and I'll find the line for 24 degrees C. I look over and it comes in at 1.116 bar, which I convert to 111.6 kilopascal. So at this point I could calculate the P average. That's just the 600 plus 111.6 divided by 2, and we come in with the average pressure of 355.8 kilopascal. Well, we have to get the specific volume initial right here. Well, that specific volume at state 1 is V sub F, almost wrote V sub G, V sub F plus the quality times V sub G minus V sub F at that line of 24 degrees in table A10. And so we calculate 0.1642. And then we go and look, well, what about state 2? Well, they don't give us a quality, but look at the pressure and the temperature. We suspect it's superheated, and we'll calculate the properties by using the state principle, knowing pressure and temperature. And then we would find that this temperature and pressure are in a pressure block on table A12. And from that pressure block, we read off that the specific volume is 0.05402. So yes, the volume did decrease, and so this is an appropriate illustration that the small volume is smaller. It looks like it went down from about, if I would estimate it, to a third of what it initially was. So maybe I'd even have to show this as even smaller, maybe put another big old weight right there, piston sealant, and then put this as a smaller volume. Okay. We have those two specific volumes, so we can substitute numbers in here. So our P average is 355.8 kPa, kilopascal. And our change in volume, it's our final volume, 0.05402 minus 0.1642. And those are meter cubed per kilogram. And then we remember our unit conversion, that a kilojoule is a kilopascal times a meter cubed. That cancels kilopascal, cancels the meter cubed. We're left with kilojoules per kilogram. And because this first specific volume at V2 is less than V1, then it's negative, and we calculate our final answer, that the work 1 to 2 per unit mass of the refrigerant is the negative 39.2 kilojoules per kilogram. And we pause and we look and we say, what does that negative sign mean? That means it's being compressed. The system, being the refrigerant, isn't expanding and pushing back the face of the piston. It's being compressed by the face of the piston. So it's a negative work. It's not out of the refrigerant, but it's into the refrigerant. Okay, now we'll go to our first law. And our first law of thermodynamics is our energy balance for the process going from state 1 to state 2. And we'll have that U final minus U initial is equal to Q 1 to 2 divided by mass minus the work 1 to 2 divided by mass. Okay, and we look at this and we say we just calculated the work per unit mass. We're looking for the heat transfer per unit mass. Can we get those internal energies? And yes, just like we got the specific volumes, we can get those internal energies. So the internal energy at state 1, here I need to scoot down just a little bit. So U1 would be U sub F plus the quality at state 1 times U sub G minus U sub F. And so we calculate that internal energy is 203.85. Okay. And then you look at the same table A12, you just look over at the adjacent value close to V2 is U2, and so U2 comes in at 349.23. Both of those have kilojoules per kilogram. So the answer, Q1 to 2 per unit mass, is equal to, we bring that work to the other side, W1 to 2 per unit mass, plus U2 minus U1. I need to scoot down just a little more. And then when you substitute numbers, Q1 to 2 per unit mass comes in at the, well, I could put the values right here. It would be a negative 39.2 plus 349.23 minus 203.85, and we're left with 106.2 kilojoules per kilogram. So it's a positive heat addition during that process. So there you go. It checks with those answers that were given for this problem. It's a little conceptually difficult because the only way that you can get it to be heated and still being compressed is that there has to be increasing pressure, and that pressure goes up. There's only one good way or logic way I can think of to put it, and that's just keep on adding mass. Slowly add mass as the volume gets smaller and smaller and smaller, and then that'll give you that, you know, that linear relationship between pressure and specific volume. Well, with that, I'll go ahead and stop. Thank you for your attention.